All right. So anyway, all right. So suppose the second partial with respect to x is 9, the second partial with respect to y is 4, and the mixed partial is 6, and AB is some critical point of f of xy. Does f of xy have a relative max, a min, a saddle, or is there insufficient information? So first thing that you're going to want to find is your D. So, and I loved that Ms. Arsland, I'll pause and tell you what her job was, but anyway, that she, when I asked, because I hadn't even really thought about what does the D stand for, and when I said, is it determinate, is it discriminate, and she said it's kind of a mix of the two, and I'm like, okay, well, that's good. So, because it kind of makes sense for both kind of apply. So anyway, so D equals, so you have 36 minus 36, which gives you 0. When your D is 0, you end up having an inconclusive critical point. So then you really just need to look at the graph. All right, good. So which is what you all got. So the second one, ditto, except now our second partial with respect to x is negative 9, and then we have times 6. You get negative 54 minus 100, which is very much negative, and when your D is negative, you have a saddle point, right? So D is positive, you have a max or a min. D is negative, you have a saddle point. When your D is positive, where you have a max or a min, then if your double x is positive, you have a min, and if your double x is negative, you have a max. Okay. All right, good. So, ooh. All right, so today, this is just one of those days. This is not 13.8b. This is 14.7b. 14.7b. Okay. And I don't even care if this goes on the video. I have not had 5 seconds to look at today's lesson, so let's just hope that this goes okay. I know how to do it, so that's good, right? You got that going for you. But I really honestly don't remember what problems we're going to be facing today, so we'll see how it goes. You should be. All right, so absolute extrema with 2 variables. No yawning. Okay, here we go. Wow, that's a lot of words.
All right,
okay. Okay, I remember adding these notes on last year after doing this lesson for the second semester because walking through problems just didn't clarify it enough. So these are steps. I'm gonna talk you through these steps right now, and then we'll see how this works in a problem. So step number 1. So you're finding absolute. This is absolute, kind of like last year you did absolute extreme on a closed interval. Last year when you did absolute extreme on a closed interval, you found your critical numbers and you tested your critical numbers and your endpoints, right? Well, now we don't have a closed interval, we have a bounded region. So now we have to test our critical numbers and all of the values along the boundary and the intersection points if there are multiple boundaries. So we have 3 basic things to test. So first we test our critical numbers, then we test our boundaries, and then we test our intersection points of the boundaries. All right, so because when you test your boundaries, you're actually testing critical points on the boundaries, right? And then you have to then you have to test your endpoints of your boundaries as well. All right, so step 1, find the critical points. That is where your first partials are both equal to 0 at the same time. For all of these, all you're doing, there's no D's. You don't find D for any of this. You're just finding the biggest Z value and the smallest Z value, and it has to occur at a critical point or on a boundary. So because of that, we're just going to we find these points and we plug them in, and whatever is the biggest is the max, and whatever is the smallest is the min. So the first points that you plug in are your critical points. So you find your critical points and you plug them in and you get your z values. The next thing you do is you're going to find the equation of intersection of each boundary with your surface equation. This is easier than it sounds. It's not that bad. So I'll show you how to do it. It's really easy. So you find where each, you get this equation of intersection, kind of like a curve of intersection of your boundary with your surface. And then you find the critical points of that curve and you test those. So next you're finding the critical points for your boundaries. I just want to call them critical points for the boundaries. So critical points for the boundaries. And then you test these by plugging them into the surface equation. And then the last thing that you test, which I used to call the corners, I kind of like calling them the corners. So it's where the boundaries intersect each other. So kind of like we used to test the endpoints, now we test the corners. All of these points that you find, you just plug in and find your z. So every one of them, you plug, so you find your critical points, find all the z's, find your boundary critical points, find all the z's, and then find your corners and find all the z's. And then once you're done, your biggest z value is the max, your smallest z value is the min. There is a warning. It's funny, this font makes it look like the Surgeon General warning on cigarettes. So, warning, make sure the points you test are within your bounded region. Because especially once you get into your boundary, your actual boundaries, when you, if you have some equation of a boundary, if you find the critical points on that function, they might not necessarily be within your region that you want. So you do have to kind of be aware to make sure that the points you're plugging in are actually inside of your bounded region. Sometimes it helps to have a quick little sketch of your bounded region somewhere like in the corner of your paper. Just so you know, like you can look and see, whoa, my bounded region only goes from x equals -2 to 6, and this is x equals 25. I do not test this thing. Yes. It's like the person in charge of health for the government. I don't know, like. Somehow I don't think the Surgeon General actually wrote the statement about testing your critical values within your bounded region. Yeah. Okay. All right, you ready to try one?
No, I need like 10 seconds.
Okay. Okay, everyone good? All right, so here's our first one. Oh wow, I almost want to do this from scratch instead of redoing the reveal. But anyway, find the absolute extrema of f of xy equals 2x minus 2xy plus y squared, bounded by region R, which is the region in the xy plane bounded by y equals x squared and y equals 1. I'll give you a moment to copy, and then we'll start walking through it. Once you have the problem written, then the first thing, if you are just waiting, go ahead and find your first partials. Okay, so my first partial x, I got 2 minus 2y, so which is 0 only at y equals 1. For my first partial y, I get negative 2x plus 2y, which is 0 whenever y equals x. So the only critical point is what? 1, 1, right? So your first critical point is 1, 1. I am a test as I go kind of a person. Some of my students last year like to kind of store all the points they were going to test kind of in a little box off to the side. That's fine. If you want to kind of write like, you know, I used to make you guys put like test, and then you would list all your different function values, right? So if you want to have that and just, you know, keep a list of your points to test, that's fine. The way that I do it is I go ahead and, here, this is, I go ahead and test it right here. So right away. So my critical point is 1, 1. So I want to go ahead and plug it in right off the bat. So you get 2, minus 2 is 0, plus 1 is 1. So that's my first value. And then what I do as I'm writing is I put a box around it so that I know, all right, that's a tested z value. All right, so that's part 1, is testing your critical points. Part 2, now we have to test our boundaries. So the first boundary we're going to test is y equals x squared. So when you're testing y equals x squared, all you have to do is replace all of your y's in your z function with x squareds. So to find the intersection of y equals x squared and our f of xy, just replace your y's with x squareds. And then here, I'll lift it up a little bit, and then rewrite a new function.
What did you do again?
So our first boundary we're going to look at is y equals x squared. We want to know where this boundary intersects this surface, so you can just do a substitution on it. And that's what you're going to do with all your boundaries. You're always just going to do a substitution. All right, so I always write it out. I write like this is f of x comma x squared. And there's my new surface function at the boundary. Now what we're doing when we are finding, testing our boundaries is now this is actually on the surface, right, along that line. So we are actually finding maxes and mins of this guy. So we're back to like Calc 1. So all we have to do is, since it's just single variable, is find f prime, set it equal to 0. So go ahead and find f prime. So I got 2 minus 6x squared plus 4x cubed. In all honesty, I'm guessing that I used a calculator. I don't think I figured out 1 and -1/2 by hand. On your homework and on your test, you might have to use a calculator to solve some of these equations. So there will definitely be some where the answers are decimals or weird fractions. Okay. So anyway, are you all okay with this? So now we've got critical numbers 1 and -1/2. We need ordered pairs. Be careful, because the ordered pairs based on these x values, you're not plugging into y equals x. You're plugging into y equals x squared, right? So your y value at this point it's not like this is 1, well, this one is 1, 1, but you're plugging into y equals x. You have to plug it into the relation that you use to get it. So we used y equals x squared to get this. So our points would be 1, 1, or -1/2, 1, 4. All right. But you know what? You don't even actually technically need a y value, because you can just, this is your surface in terms of x at that point anyway, so you can just plug into that. If you find a point on your boundary and it's a repeat, like we'd already tested 1, 1, you don't have to test it again. I mean, I can see it's a repeat. So if you don't want to test it, it's fine. But this is a new z value. Vikram, do you have a question?
No, I just answered it.
Oh, okay. Thank you. Okay, we have one more boundary to check. The second boundary that we have to check is y equals 1. So now, instead of changing all of your y's to x squareds, you're going to change all of your y's to 1s. So now to find your intersection of your second boundary, you're going to replace in your z function, you're going to replace all of your y's with 1s. And then we're going to do the same thing. Find the derivative, find the critical numbers, and test them. Except that you really don't have to, because your function's pretty much stuck. So every single point on our second boundary is 1. So there's really nothing to test, because the z value for every single point on that boundary is 1. And we've already got 1 listed anyway, so we're good there. All right, so we have tested. Let's just make sure we understand. We tested our critical points from our partials, right? Then we found the intersection of the surface with our boundaries, found those critical points, tested those. The last thing we have to do is test the endpoints, which are really kind of like the corners. It's the spots where the boundaries intersect each other. So the boundaries intersect each other at wherever x squared equals 1. So at x equals plus and minus 1. So you would have, and they have to fit both of these equations. So you end up with the point -1, 1 and 1, 1 to test for your corners. So your corners are the 2 points of intersection of your boundaries. So the 3 things you test: your critical points you found from your first partials equaling 0, the critical points that you found by finding the intersection of your boundaries and your surface, you find those critical points, and then your corners. Once you've tested, like plugged all those into your main function and found all your z-values, before you write your answer, there's one more thing you should do a quick check on, because this is a gotcha, and that's to follow that warning on the last page. So our boundary looks like this. We've got y equals x squared and y equals 1. That's our bounded region. X goes from -1 to 1. And y goes from 0 to 1. All of the points that you test have got to be somewhere in this closed region. They can be on the border, that's fine, but they have to be somewhere on here. So if you got an ordered pair where x was -2 or where y was -3, it doesn't count. It's not part of our max or min because it's not part of the part that's enclosed by this bounded region. So check, always do a last minute check to make sure. 1, 1, that one's fine, right? Let's see. -1/2, 1/4. So we're at -1/2, 1/4. That's fine. It's actually on this boundary. Let's see. 1, 1, -1, 1. Those are all fine. So you do a check to make sure everything is fine. Once you've done your check, the biggest number you found, z-value you found, is your max, and the smallest z-value you found is your min. Yes, well, it depends on what the question is.
So would it 1, 1 or -1?
Well, the max is the max. The max is the highest z-value, and the min is the lowest z-value.
Yeah.
If I say where do they occur, then there would be multiple places.
Okay.
You ask us where they'll occur?
I don't know. Do you want to see this in Grapher or no?
Yeah.
Yes? Okay. All right. So,
Are you able to explain what the boundaries are in the
I don't know. Let's see. 2x minus 2xy plus y squared. I might be able to kind of sketch it a little bit. Miss Arslan was really impressed with Grapher. She really liked that software. She was bummed that when she found out it was only an Apple software. Okay. All right, so 2x minus 2xy plus y squared. Woo! Before I do anything, I've got to get this checkerboard out of here. This is going to make me crazy. Uniform. That's kind of nice. Do you want me to change the color? Make it a little more red. Okay. All right. All right. So here's our graph. And, all right, so this is actually oriented. There's the positive x-axis. There's the positive y. There's the positive z. We are only interested in the part of the graph that is over the region of
bounded by y equals x squared and y equals 1, which is a region actually, so from underneath it would be like this parabola. I don't know how to graph it without, here. Okay, wait, let me just hold this still like this. That region. It's turning. It's no longer that region. Anyway, so over some region here, this like some kind of cutout. So 1, 1, which would, and negative 1, 1, did those both give a 1? So those both gave pi points. So, yeah, I can't get it to orient right. So anyway, it's somewhere like here and here. Somewhere here and here, it must have the same z value. There's kind of a symmetry, but the problem is that it's over that bounded region. It's really hard to say without actually like graphing the bounded region. If I graphed it, you know what I could do? Maybe I could put it in. Let's see, x equals t squared. Negative 1 to 1. That'll only put dots, won't it? I wonder if I can go like list values of t. Negative 1, negative 0. Can you see it? Did it graph? No, it's not liking it. Yeah. I don't know how to do it. I don't know. I'm giving up on it. I'll see if I can find a better way. Change the appearance of the boundaries to be a solid color. Oh, you know what? If I just graphed them regular, I wonder if it would work nicely. All right, one more time, and then we're going to move on to another problem. All right, so let me add a new equation. Yeah. There. Okay. Oh, that's not bad. Because then you can see it kind of like that, right? So these are our boundaries, right? So that's the bounded region that we're finding the max and min of this function on. And what we figured out was everywhere along this boundary, apparently the z-value is the same. And so here and all along here had a z-value of 1. And then somewhere, I don't remember where, it was somewhere on this boundary, there was a z-value that was our min, our negative 1. It's probably like somewhere over here would be the low z-value. Does that help a little? Kind of? Oh. All right. Woo. Anyway. All right. So that's the way to look at it. That works. All right. Next one. All right. To find absolute extrema in a closed bounded region, we're going to use a method similar to find. Oh, that's just, I don't know why instead of endpoints test, we have boundaries. I don't know why I have that there. It's almost like this would be the first problem. All right. So, oh, okay. So your book likes to present ones where the region bounded is actually a rectangle, and that's what we've got here. So we have z equals sine of x times y on the closed interval where x is bounded from 0 to pi and y is bounded from 0 to 1. All right, so take a minute first, find your first partials. One critical point is the point 0, 0. And if you plug 0, 0 into your function, you get a z-value of 0, right? So f of 0, 0 equals 0. The other, it's not really a point, but it's kind of a relation, is you end up with xy equaling pi halves, right? If you get xy equals pi halves, and we just plug that in here, f of wherever xy equals pi halves, you get the sign of pi halves, which is 1. So, okay. So I don't know how I worded it down here. Looks like I did pretty much the same thing. Yeah. Okay. Oh, I solved it for y and wrote y as pi over 2x. So I did x comma pi over 2x. Plugged in. Anyway, so you get 1. All right, so that's based on our first partials. Then you have to test your boundaries. Testing the boundaries when the boundaries are constants just means you replace whatever variable with whatever constant and see what happens. So the first one would be when x is 0. So you replace your x's with zeros in your function and see what, find your maxes and mins there. But in this case, if we replace our x with 0, we just get sine 0, which is 0. So all along the boundary x equals 0, we have a z-value of 0. If we check all along the boundary of x equals pi, we get sine of pi y, and that can alter. Let's go back, and if y is 0, we end up with sine 0 is 0. So this is all 0, this is all 0. This could be something different, and this could be something different. So really the only two boundaries that we really need to look at are this one and this one, where x is pi and where y is 1. All right, so if we check where x is pi, you just replace your x with a pi and you get sine of pi y. And so then you do your derivative, find your critical points, and you get y equals a half. Which makes sense. Like, a lot of this is silly because we know on the interval from 0 to pi that the max of sine is going to be 1 and the min of sine is going to be 0. It's not going to go negative. It's easy peasy, right? I mean, we don't really have to do any work at all because this is silly because we know the max and min of sine. But if we were to do the work, so then our first one would be where x is pi, replace the x with a pi, plug it into your z function, find your derivative with respect to y, set it equal to 0, and solve, and you get y equals a half. Then you plug the point pi a half in, which is the sign of pi halves, which is 1. Then you test your other boundary, which was y equals 1. So now you have f of x comma 1, which is sine x. So then your derivative is cosine x, which is 0, again at pi halves, and you end up with f of pi halves comma 1, which is the sine of pi halves, which is 1. Is that in our interval? The last thing that you're supposed to test are your corners, but we just tested them. Did we test the corners? Did we test pi 1? Let's see. So we know this is all 0. We know this is all 0. So the only other corner that we have to test is
f of pi 1. And f of pi 1 would be the sine of pi, which is 0. Yes.
So when you're plugging in like pi half, 1, which one are you plugging that into?
Every time I'm testing a point, I'm plugging into the z function, my original function.
Okay. So then how did you find the x equals?
Tell me which one we're
Sorry,
talking about.
the right under the first test. You can just explain that stuff. The word test.
This?
Yeah, right under.
Right here? Oh, okay. So let's see. I'm going to just rewrite. The boundaries were x 0 to x to pi and 0 to y to 1, right? So I have to test at x equals 0, so I do 0 comma y, just replace my x with a 0. I have to test at y equals 0, so I do x comma 0, replace the y with a 0. Then both of those just always give me 0. So then I'm like, all right, well, let's test x equals pi. So I replace my x with a pi, and I check f of pi comma y. So what you get when you do that is you're finding where the line x equals pi intersects with your curve. And so if you find the critical points of that function, you get like the max and min along that line on your curve. So you get y equals a half, and then, so your x is pi, your y is a half, and then you plug that into your z function, the original z function. You can actually plug it in here because it's going to be on the same z, it's just along that line. And then the last one we had to test was y equals 1, so x stays x, y goes to 1. Plug this into your original function, get your intersection, find your derivative, set equal to 0. There's your critical point. And so now we already had that y was 1, x is pi halves, so you're testing the point pi halves 1. Again, in the original function. Always in the original function. Every single time, though, we kind of know, I almost should have just skipped this problem, because we know the min is going to be 0, and we know the max is going to be 1. But anyway. Yeah. Well, we're going to do another one.
I want to see that graph.
Okay. No, we're not going to do the graph.
You go back first.
Yeah. So it's the same, this is the same process, but it's kind of a simplified problem. The next one is nice because it has constants, the boundaries are constants, but it's a different function, so you don't know the answers. So the next one kind of puts it together. Although the first problem, in my opinion, was my favorite. That's the one I would put on the test if I had to pick. All right, are we good? Okay, last one of the day. We got 14 minutes, plenty of time. We're going to find the absolute extrema for f of xy equals x squared plus 2xy plus y squared, where absolute x is less than or equal to 2 and absolute y is less than or equal to 1. When we say absolute x is less than or equal to 2, that's just fancy talk for saying what?
That's a 2.
So the first thing I want you to do is find, once you write the problem down, is find your first partial. All right, so we've got our first partials, which I saw everybody got, at least all the people that I was just watching. So you end up with y equals negative x, right? That anywhere on that line, both partials are equal to 0. So every single point on that line is a critical point, which means if you plug in that relation into your original function, you should end up with something interesting happen. So I replaced my y in my f of xy with a negative x and found what is f of x comma negative x, which ends up being 0. So the z value for every single point along this line is 0. We don't know if it's a max or min, but it's something. Next, we have to test our boundaries, right? Okay, so I probably started with -2. Yeah, okay. So, yeah. So when x is -2, I find f of -2y. So I just replace my x's with -2's. And I find the critical points of that function. So you find your derivative, set it equal to 0, solve, you get y equals 2. And then you plug in the point -2,2 to see what your z value is. Ooh, except -2,2 is outside of our boundary. So I didn't test it. What? Okay. So then I should test x equals 2. At x equals 2, I get y equals -2. Also outside of our boundaries. Don't have to test it. Next, I'm going to check y equals -1. So now I'm going to do f of x comma -1. So f of x comma -1. I find my function. I find my derivative. I get x equals 1. That's in my boundaries. So now I'm going to find f of 1, -1, because my x is 1, my y is -1, and I get a z value of 0, which makes sense because, of course, 1, -1 is on the line, y equals -x. All right, last one. I'm going to test y equals 1. At y equals 1, I get x equals -1. I don't even have to test f of -1, 1, because I know it's on the line y equals -x, and it's going to be 0. I've tested my critical points. I've tested my boundaries. The last thing I have to test are my corners. My corners, I have 4 corners here, right? So I have -2, -1, -2, whoops, let's see, 2, -1. Then I have -2, 1, and -2, oh my gosh, I can't do that. 2, 1. Okay. So I have 4 corners to test. Just plug each of your corners into your function, right? And just see what you get. So my 4 corners gave me z values 9, 1, 1, and 9. I've tested my critical points. I've tested the intersection of the boundaries with the surface. And I've tested my 4 corners. Once I've done all those tests, I'm ready to determine the max and the min. The only numbers that I have boxed in are 0, the z values of 0, 1, and 9. So my min is going to be 0. My max is 9. And that's that. And there's some beautiful graph of this thing, which kind of looks like a piece of paper we folded in half. Tomorrow you'll be doing this same thing along with other stuff that you learned in this unit on a quiz. I would be happy to Yeah, I'm going to turn the recorder off.